So we are discussing about the selection combining. So what we have done in the selection combining, we have selected the max antenna for we are receiving the maximum signal to noise ratio. And this is how we are improving the reliability of the signal. Now we can also calculate the probability of defeat event for the selection combining. So now you can see here we are selecting the maximum one. So now we can see gamma sigma is nothing but the max of the signal to noise ratio ML or an antenna. So now if the maximum one is greater than the so obviously that maximum will be also lesser than this one. So we can use this one signal to noise ratio is lesser than the noise power. And we are getting this result. E raised to minus e raised to minus 1 by gamma bar. Right. If we want to look at minus e to noise ratio, we are getting this expression. One by gamma bar raised to 1. So now probability of phase shift event is getting reduced and it is decaying at rate and okay. So now earlier case when we have used the signal antenna, probability of phase event was 1 by gamma bar. So for example, gamma bar is 110. So probability of phase event is 0.1. But if we are using mining, so what is the probability of deep feed event is 1 by 10 raised to power square means 0.01. So this is how we are reducing the probability of deep feed event. Okay. Now the next one. The next one is the maximum ratio combining. You can see in the figure. Okay. So here maximum ratio combining. There are n number of antenna elements. There are n number of signals are arriving at the and receiving antennas. Now, after this signal is received, it is multiplied with weight C1 at antenna 1. Now, the same signal is multiplied with C2 after being received at the antenna element 2. And so on. And after that, these all signals are combined together and we have got the resulting signal. But what is the problem? How to get all these weights C1, C2 up to Cn? What should be their value so that we can maximize the signal to noise ratio because these are the code maximize the signal to noise ratio. So now we are coming to the here is the input output system. So this is the y equal to fx plus w. And is a vector here because we are having n number of antenna. So size of the x vector is n cross 1. It means there are n number of elements in the array. X signal is x and w is the AWGN vector because at each antenna element there will be a noise. So there are n antenna elements, so there will be n number of noise elements. Okay. So noise y is the received signal and the receiver signal. Now we have to combine all the signals. See, y is the receiver and c is the containing the weight of the in which the received signal is multiplied. Here you can see that. So here you are receiving y1 is multiplied with c1. Here you are receiving y2 is multiplied with c2. And here you receive y1 multiplied by c1. And they combine. So the same process we are doing here. C Hermitian into y. Okay. C is the vector, y is the vector. The size of y vector is you will get the resultant signal T Hermitian. Now this is a signal power and this is a noise power. So now signal power divided by noise power. So this is my signal to noise ratio in the maximum ratio combining technique. Okay. Now here we have to maximize this signal to noise ratio under this constraint. C is equal to 1. This is noise part. W is the noise part, and we are doing the some processing at the receiver side by multiplying Hermitian with the receiving signal by. So if you are multiplying Hermitian by, it is multiplied with the signal part as well as with the noise part. So it multiplies noise bar, but I don't want for the noise to be amplified. So what will I do? I will put this constraint. Okay, this should be a C vector should be a unit vector. So this is a constraint. We are putting C harmonic into equal to Y, and we are maximizing the signal to noise ratio. Now this is my problem. So now after solving this problem, I will get my C vector, which is H norm H. So this is the norm of x is under root x1 square, x2 square, x2, xn square. This is known as norm of x. So now you can see c equal to x by norm x. This is my base. We can use as a symbol to commute signal in the optimal way. Now we can see the signal power mod of h square, norm of x square into p, and then noise power sigma square. Now we know that what is the signal to noise ratio? Q of under root 2 signal to under root gamma. Q of under root gamma SNR. So now signal to noise ratio. Now you can see Q of under root norm of x square into P by sigma square. So P by sigma is the transmitted power. Now as a receiver side, you can see we are receiving the power. We are calculating the receive signal to noise ratio. And this mod of h square because of this one. If signal to noise ratio at the receiver side is fluctuating because now was H is a random quantity. This random quantity is always changing. Okay, but we have to find the average signal to noise ratio. Here we can say average quality of electron. So we have to average this expression. So for averaging this expression, we should know the what is the distribution of norm of H square. So now you can see norm of H square can be written as mod of H1 square, mod of H2 square, and so on. This is a new random variable which is equal to Z. Okay, so Z is another new random variable which is known as chi-square random variable with 2n degree of freedom because as a complex number, so complex number is having a real part as well as imaginary part. So there is 2 degree of freedom. So that's why they have n elements. So total number of degree freedom becomes twice of n. Okay. Now this is a PDF probability density function for this random variable Z. And finally, we will averaging the this average for this instantaneous probability of error with respect to this probability of density function, which is Z here. Now finally, we got the expression. This one. This is the closed form expression. Okay. Our probability of error. So this is the whole one. Okay. Now we can simplify it further by considering the high SNR. So when you consider high SNR, lambda equal to under root gamma equal to 1 plus gamma. So this 1 minus lambda approximated as 1 by gamma when this gamma is very greater than 1. It means the signal to noise ratio is very high. Now 1 plus gamma is approximated in E2. Now finally we'll got this expression for probability of error. Now at that if you see the probability of error expression, which is directly proportional to 1 by gamma raised to power. So what was the earlier expression for the probability of error? It was 1 by gamma. Now we got 1 by gamma raised to power 3. Okay. Now the probability of error is getting reduced at a very fast rate and this is the rate at which the probability of error is getting reduced. Now we can do the simulation for this one. So I have shared this code with the sir. You can call Dr. Rao and you will share code with the students. So basically, I will, running this code for less number of iteration, otherwise it will take more time. So you have got the code. Please try to run this code on a screen. You will get the results. So I have only code for less number of iterations. So the curve is not perfectly smooth, but we can, you know, get the result. So now you can see we are getting three plots. Okay. The red one is corresponding to the when the receiving antenna is equal to 1, and the blue part is corresponding to the when the receiving antenna is equal to 2, and the red one is corresponding to the when the number of receiving antennas are 2. Now it is the difference. So when we are getting radio, when we are increasing the number of receiving antenna at a 51 level. This technique is known as multiple radio combination. Multiple radio combination is simply multiply the received signal with the base and base of complex, and then after these signal being multiplied with the base, and finally they are combined together to get the resultant signal. Okay. So now let's go to the code. This is the result. So I hope you guys have got the code. You will got the code. So now coming to the main part only, coming to the combiner, there will be written combiner. Okay, I can commented on the code. Easy for you. Okay, it is written combiner. So combiner is nothing but we are calculating the weight. Weight, we need the signal value of multiply. C1 and C2 आपको so C1 की multiply करें. C2 की multiply करें. Even to y1, simply what we are doing. C is the we are getting the dot product of these two vectors. Okay. So now here add this line CH. It will be written in the code CH. If you see the code, it is written, it is nothing but this is combiner. Okay. And the after getting the combiner, it is written here in the code combining. The combining part, the dot product in the signal, and finally we are getting the resultant signal. Now let's process we will do annotate like we did for relativity channel, and we can increase the probability of error. Okay, and here we have at this line you can see last one. It is written theoretical probability of error. We have integrated the simulation result. Okay, otherwise we cannot say that there is a correct or wrong on simulation result. So to release the simulation result, we have to implement the theoretical operation. Theoretical expression. Okay. So I hope you are there. Okay. The rest of the thing is going to plot the okay. To get all these plots, and these are the final results. Okay. So now here we have plotted the whole. You can see the red part. This red line is for simulation one, and this blue circle is for the theoretical one. So all the results, this theoretical one and the simulation are matching with each other. It means my simulation is correct. Okay. So now equal to 2, you can see here this blue part, and now you can see this, this is brown circle. So brown circle is corresponding to the critical expression, and this blue line is corresponding to the this one. So we can for another two. So both of them matching with each other. So it means our calculation is correct. Okay. So now for as we are increasing the number of receiving antennas, the probability of error is getting reduced. Okay. So this is the maximum ratio combined, and it is used okay in today's wireless communication systems. Now we are moving towards next one. Now we can also calculate the probability of defading for the maximum ratio combining. So here we can see this is the signal power and this is the noise power. When the signal power is lesser than the noise power, this is my probability of degree calculate the noise power is lesser than the sorry, signal power is lesser than noise power. And finally, we are getting this one. Probability of Z less than 1 by gamma bar and Z is nothing but normal by square. Chi is the variable of which provides degree of freedom and this is the multiplication function for time square random variable. Now you can see finally we have got this expression. So this is the final expression we have got. Now for highest NR, because I want to see the effect of the yeah, we can see the performance of the deployment scheme. So I can simply find this expression for the highest NR. So I am taking the highest NR. So now it is coming as 1 by centurion and gamma raised to power n. Right? So now okay, related for single channel it was 1 by gamma bar. Now it is 1 by centurion and gamma bar 1 by gamma bar raised to power n. So this is how we are getting the probability value and it is we can add a rate. Okay. We can also do the code for this one. So this is for selection combining. I should tell you that probability of defading. So first of all, we do the probability of defading for the selection combining. So let's run this code for less number of iterations. Let's get this code. Sir. Sir, I mentioned one more indication just next. So now we have got the result probability of defading for the selection combining. So this is a result for probability of defading. The probability when the noise power is greater than the signal power. Okay. So now you can see we can look at for the different when the defading is equal to 1. So these become the equation between the simulation and the okay. So now for example, the product is minus 3. So this is approximately 1080. Then we have given the number of participant data is equal to 4. Now we do this part. So it is coming from I think 1580. So 1580. So if you take that, the same data number is equal to 2. Minus 3. 1580. When we do number 4. D3 is called minus 6 is equal to 10 degrees. So there are 6 degrees difference. If you keep on taking the number of 3 degrees and the same it will give less probability of D3. We are reducing the probability of D3. Okay, this is good for the system. So there in the code is already shared with you. So simply we are choosing the channel. Okay, the channel it is very strong channel because It will be maximum general gain. Even people make a channel the index, and then finally we are calculating the received signal power and the noise power, and we are calculating the number of gates. How the signal power is the signal power, noise power is the signal power. Okay. For example, we have 100 channels, 1,000 channels. So out of 1,000 channels, we have to check that how many times my signal power is lesser than the noise power, or we can say the noise power is greater than the signal power. So we have to calculate all of those such events. We have to divide the total number of events. Okay, then now we can get the probability of each event. Okay. Now the same we can do MRC this one. Earlier code I explained that was for equal gain combining. Okay, this is for max. Okay, I think okay that is what okay. This it was for selection combining. Okay, now I'll share the code for the maximum ratio combining that we have studied just now. So please wait a minute. So now you can see the performance. So this is for maximum ratio combining. Okay. So now you can see for maximum ratio combining the same as selection combining. I have taken number of 15 of 1 and 2 and 4. Then I calculate it and then compare with the theoretical ones for less number of iterations. So that's why there is a little deviation between the theoretical one and the theoretical one. Okay. So now you can see here also the theoretical is reduced when we are increasing the number of receiving antennas. Okay. So here also we have to calculate the noise power. So first of all, we have to calculate the noise power. So here you can see in the code is here we already read you. In that code, there is written combiner. So we have to calculate the combiner. Okay. After calculating the combiner, we have to combine the signals using the combiner. So here we are combining the signal. Okay. And after that, this is the combiner signal. Okay. And this is a noise power because the combiner part is done at on the noise also. Uh, and then after that, we have calculated the noise power and the signal power. And then we are calculating the all those events where the signal power is less than the noise power. And then we have seen the number of events, then calculating the equilibrium. Let's see the last scale configuration here. Equal means combining. So what we are doing equal, it is same as maximum ratio combining, but there is a little difference here. Here it is a case. As a case, okay, in the equal being combined. P is a complex number, and complex number is having a amplitude as well as the phase part. But here we are purely using only the phase part combined the signal. Okay, so now here for J51 is multiplied with the signal received at the first receiving signal. So 1 into E into J51 into E into J51. So finally, all the signals are being added and then we got the resultant signal. So this is known as equal maximum ratio combining. But right now we have we have reduce the complexity of the but we compare the performance whether it is either Amartya is combining. Okay. So here okay. So now you can see here, this is an input system that you can use for signal network. This is the way these are the way we are using in equivalent command. So as one is a complex number, as one is trying to get A1 into E raised to power J1. Now what is the mode of H1? Mode of H1 is nothing but amplitude only. So what is the amplitude of H1, which is A1? So A1 into this is A1 into A1 into E raised to J5 divided by A1. So what remains here? Only E raised to power J5. So now this is how we are multiplying this thing and it is the single data. Now we have to combine all the signals. So this is the process by which C has mentioned into Y. We are finding the signal. We are taking the dot product of the C signal and the combiner C. And finally, we got the expression. This is a signal power, and this is a signal, and this is my noise part. Now we can calculate the signal power and the noise power separately. So now we have calculated the signal power and it is the noise power. Okay. Now we have seen, first of all, we have to calculate the noise power because in the MRC we have always take here that amplifier. That's why we put constraint on the final. Here it's not any constraint on the combiner. So it may amplify the noise power. So now you can see here when we calculating the noise power, it is enhanced, it is increased by n time. Earlier it was sigma square, now it is 10 into sigma square. Now finally we can calculate the signal to noise power. So this is my signal power, Z into P, and noise power is N into sigma. And what is Z is here? Z is nothing but sigma from N to N and sum of and then at bottom HN. Okay, and this whole expression. Okay. Now we can easily compute the probability of error. We can see here. Probability of error, you can evaluate this expression with respect to the probability density function of Z. But to get the probability density function of this random variable, this is Z here, which is very difficult. So that's why we cannot analyze the theoretical expression of probability of error for equal get combined. Then how evaluate the probability where we can evaluate the probability of error using the Monte Carlo simulation and the numerical integration. Okay, method. So now we can do the code for this one. So I have shared the code. So let me run this code also. And now we have the selection combining in which maximum and minimum sector correspond the maximum signal ratio. Second one is maximum ratio combining. In the maximum ratio combining, all signals will be combined together in optimal way. And the equal when combining, the signal are combined with, in such a way that the signal will be co-phase with each other. Okay. So now you can see we got the results. Okay, so now you can see two, this is two plot. We are comparing with the acceleration component. So so now we can take the values corresponding to the experimental and acceleration term. This is corresponding to the so they are matching. Okay. Now, when we increase the number of receiving antennas, so red one is corresponding to the equilibrium component, and the blue part is the corresponding to the maximum ratio component. So, which one is better? Lower one or upper one? Yes, our goal is to reduce the quality of air. So now which one is good? Upper one or lower one? Low part or red part? This red one or blue one? Which one is better? Anyone? Anyone else? Blue one is better. Blue one is better. It will be blue. Which one is better? Blue one. Yes, blue one is better because it is blue one. But if it is for state or not, we will be getting the lower probability of error. Okay. So now you can see it means MRC is giving good performance compared to the equivalent component. Okay. Although equivalent component is easy to implement. Okay. Compared with the MRC. So now we will have M equal to 4, number of receiving of 4. Related to equivalent component and the low part is exponential component. So as they increase the number of receiving data, the probability of error is getting reduced for equivalent component, but at the same time, the performance of the MRC it is constant than the equivalent component. It is better for verify you can suddenly. If you have any kind of doubt, you can ask me. So now this part is over. Now we are moving towards another new topic, which is beam forward. Okay, so now we have a figure. So now the figure we can see here. This is my transmitter. This is my signal, and here is the transmitter part, and the signal is multiplied with weight C1. Then it is given to this antenna element, and the signal is multiplied with weight C2. Then given that second element, and so on. Now we have to give these weight in such a way that the signal should be directed towards the intended user or target user. So now here you can see there is one beam, red beam is directed towards only the target user. So what is the benefit of this one? What is the benefit of this one? Beam forming. Suppose I have to transmit one signal in that particular direction. So what can we do? We have to, for example, I will design a system. The system will transmit the signal in the entire group. And another system is that I will design a system in which the computer will transmit the signal in the target user. So this one is second. Second plan. Second one is I will be consider my entire size in the entire user. So this now we can improve the signal form because in the first your customer signal exists as well. So one information is distributed. Okay. But the second when we are transferring a signal in the connection to the intensifier, the whole electric is connected to the cycle. This is how we get this is the thing concept and the unique user. So this is the concept and the case is the concept. So the promoter okay. Got it? Now we have to analyze the performance of this one. Is this clear to everyone? Is this clear? We are adjusting the weight given in the bracket. In the bracket. If you don't want to learn, you can go outside. Okay, so I hope this is clear. If this figure is clear to you, then it becomes very easy to understand the remaining part. Okay, so I will repeat. We have to adjust these weights C1, C2, and Cn in such a way that my signal should go in the particular direction. Okay, this is called the beamforming, and this concept has been used in the fourth generation as well in the fifth generation wireless networks. Okay. So now here is the system model. So C dimension into X. This is nothing but X in the figure that is transmitted. Here you can see the figure. Signal is X and there is multiply with C1, C2, Cn. So here this work is done by C1 dimension into X. C dimension into X. C1 into X. C2 into X. C3X up to C1 into X. Because there are n data element at the transfer. So each data element will transfer signal after being multiplied with the weight. Now after that the signal is passed to the channel which is H. Okay, so definition of channel is N 1 cross N. So 1 cross N means number of missing antenna element 1 and the number of transfer antenna N. Okay. Okay, so here add this here into the one display data and the n number of transparent data because VM calling concept is only possible when we are getting the large number of antenna element at the transmitter side. So now we can easily calculate the signal power and the noise power. So this is my noise power. This is my signal power. And this is the noise power, so corresponding to noise power. So signal power and the noise power. Okay. We have got the signal to noise power. Now further, we have to calculate the weights. What will be the weights? What will be the weight? This is the main problem now. Because for example, this small station can move in any direction. Because we are not this time you are sitting at your place, but it's not necessary that every time you be sitting at you will be keep moving on this go. So everything here the signal is coming towards me through the green market as well. You can move towards the middle bit from my green market and my solution and keep it away. So now again the weight needs to be adjusted accordingly. But what would be those weights? This is the whole problem. So now you can adjust these weights by maximizing the maximizing the signal power and the noise power. The same concept we have been using here. See, we provide this one C1, C2 and C8. These are nothing but these are in the direction to the signal. Correct? By changing the by these real are being adjusted, we are just giving the direction the signal. Okay, I'm giving the direction, so we should go in that direction. So that's it. Ultimately, C1, C2, C8. If you put in the one bracket, okay. So if they provide a direction only, so obviously I will choose that okay, this vector should be a vector. So now the same concept we are using. So we are putting the constraint that the C vector vector is shared. So C into C dimension. This is not correct. So this will be a unique vector. This is what I say, and the my objective increase the signal to noise ratio. Sorry. The signal to noise ratio. So I will be maximizing the signal to noise ratio with constraint that my beam following vector should be of unique norm. Correct? So now finally we got this expression mod of norm of I square into P by sigma. This is a final expression of signal to noise ratio. Okay, signal to noise ratio. Now we have to calculate the probability of error for BCSC case. So we have already calculated. So now if we compare this expression is same as M1C. Maximum resistor combined. Okay. So in the maximum resistor combined, what was the setup? It is setup. Number of continuity element was 1. Number of continuity element was n. We have reversed the load of the transmitter and the receiver. Now, the transmitter is n number of transmitter element and the receiver is only one receiver element. Okay. So, we will get the same expression and acceleration combining. Now, finally, in all the mathematics, we are getting this. This is quality of error expression. Okay. Now we can simplify it more, and we will finally get the quality of error is 1 by gamma raised to power gamma raised to power n. This is the final quality of error expression for exam. So corresponding this one, I'm going to share the code. So I have seen the code below friend. So we will see the code. All of resistance. I hope you got the code. So try to run that code. Okay. I hope this code is already shared with you. So I'm running this code. You can also run the code at the same time, so you'll also get the result in your product platform. So now you can see this is the picture from the uniform. Okay. So we are adjusting the weight at the transmitter side in such a way that my signal should go in the particular direction. Okay, let me complete that. I will do it. So now the maximum vector conversion you can see here. Okay. So number of transmitting we are increasing and the quality of error gets reduced. Okay. So this is the whole concept of the maximum vector conversion. So the code is always here. You can practice at your home. Now the next topic is the last topic. Okay, so we can also discuss the diversity order. What is the meaning of diversity order? So diversity order is something that we discuss each way and multi so here we can say that the diversity order is equal to minus limit and the large tending to infinity. The numerator part log of P and denominator part is log of SNR. If we do like this, we can get the sometime the probability is very quite complex, and we are not able to calculate the diversity order. So just the combination of probability expression, we cannot tell the diversity order. So we use this concept. So here now you can see probability of reference approximately 3 into minus 10. So here if you evaluate the diversity order, so what is the power of L? So now here we are getting the diversity L. So diversity L is there L number of parts which signal is coming. The same copy of the signal is coming. Okay. Information from your mother, father, brother, or sister. So it means the same information you have got from the four person. So if you get the same information from multiple person, it increases the reliability of the information. The same thing we are doing here. We are getting the signal from four differences from three number of channels. You know, the reliability of the information is being increased. Now coming to the last topic, which is spatial multiplexing. This is a very important topic. It is the last one. So I request you to pay attention here. So what is the multiplex? I told you that till now we have discussed the case when we are sending the same quantity of the signal multiple times from the transmitter to receiver. And we can say from between okay, transmitter to receiver. And here, and we have improved the reliability of the signal. But here in the case, we are transmitting the different signals simultaneously from the transmitter to receiver. For example, we are transmitting one signal at a one time. Okay, now and this signal duration is 1 second. So we can say, okay, so you are sending 1 bit. So data is 1 bit per second. Now we are sending 10 bits. At the same time, we can say it takes 1 second to increase by 10 times. It becomes 10 bits per second. So this is the concept of the spatial multiplexing. So now you can see in the figure, transmitter is having empty number of transmit antennas and receiver is having multiply input and multiply. So now we have to define the input relationship to this system. So I will skip this part. Actually coming to this. Okay. So this is Y1 it is a received signal at the first listening antenna. Y2 is the signal received at the second antenna element. So Y1 is nothing but this row vector is multiplied with the column vector. So H11 into X1, H12 is H2, and so on plus noise. So this is a figure. You can see the figure. So at this receiving antenna, the signal received from the all transmitting antennas, 1 to up to NT. Okay. Look at the second receiving antenna. It is receiving signal from all the transmitting antennas. Okay. So this is this is this in the form of multiplication hx plus y equal to hx plus w what x the channel matrix between the transmitter and receiver. It contains the channel coefficient of that method and now cross NT. Now x is the transmitted signal vector. So there NT transmit antenna. So what should be the should be the transmit signal vector should be NT cross 1. Okay, now W is the AWGN vector of dimension NT cross 1 because sorry NR cross 1 because obviously that the noise will be added at the receiving side. Now Y is also an R cross 1. Now finally coming to okay, what see to see the capability of the MIMO system, yeah, we can say to see the on the static and spatial multiplexing, we need to take the decompose. We have to decompose this channel matrix into the different matrix. Okay, so this channel matrix H can be also written as U sigma B elimination. And if U matrix and B matrix are unitary matrix, so if you take the elimination with their matrix, it will give it is given an identity matrix, same as for the B matrix. Okay. Now the sigma matrix can be written as this one. These are diagonal elements, sigma 1, sigma 2 up to sigma r. And these diagonal elements are arranged in a non-decreasing order. It means sigma 1 will be greater than sigma 2 and sigma 2 is greater than sigma 3 and so on. Okay. Now finally, I will do this process. Okay, pre-processing, this is known as this is post-processing. So before transferring the signal, I will do the pre-processing and pre-processing is done by multiplying the transmitted signal vector x delta with V1 and after you will receive the signal, you will do the post-processing. So for post-processing, this U animation is multiplied with the received signal vector part. And finally, if you all this mathematics, not explain this one, you will get this one. Okay, now you can see a test figure. In this figure, you will get anything number of channels. And each channel is, each channel is independent from each other. From each channel, we can transmit a signal. From all the channels, we can transmit signal simultaneously. Okay. So it means at the same time, we can transmit the empty number of signals. Yeah, we can say, for example, empty number of bits. In a simple way, we can transmit the empty number of signals. So this is the capability of the MIMO communication. It means in the MIMO communication at the same time, we can transmit the multiple number of signals. Okay. Now we can evaluate the channel capacity. So for each channel, we can calculate the signal power and the noise power. And what is the total channel capacity? Is the sum of their individual channel capacity. So this is the total channel capacity. And what is the sigma and square NT? It is the channel signal. Okay, here you can see sigma 1. Sigma 1 is the channel gain of the first channel. Sigma 2 is the channel gain of the second channel. Okay. Now we have to allocate the power. Okay. So now you can see here we are allocating the equal power to all the channels. So we have total power rho. And how many transmit antennas we have? NT transmit. So the power is equally divided to among all the transmit antennas. So the total power is sigma by NT. So it becomes sigma by NT. But what is the problem with this equal power allocation? Any problem? This is the last topic. Okay, complete. So Is the channel capacity is depending on the channel gain. What happens if this channel gain is very, it is the value of the channel gain is very low. So what will happen? For example, the value of the channel is close to the zero, but there is power to the channel. So these are wasted of the power because I channel is already works and if I pick up power, one example there are two instruments. One is good and one is good. Student. So he is very easily. If student is not good, he will not get it. Student, I am putting it. One is also there. Completely effort. The same thing we do here. Now we are going to do the next power location scheme. So in this power location scheme, water filling algorithm, we give the more power to the great channel and we will give the less power to the weaker channel. This is how we can increase the channel capacity in gate completely further. So this is the entire process. Okay, and here you can see the line. So this is known as water filling algorithm. Now you can see we are giving more power to the stronger center and giving the less power to the weaker center. The blue part is corresponding to the power. To improve the entire channel capacity, we will give the more power to the stronger channel and the less power to the weaker channel. Okay. So this is how we can improve the channel capacity. So this is the end. Now I will going for the artificial. Okay. Students continue that will complete. What we want the students cannot be able to have. Okay, then it means now we can do it. Okay, no problem. Have only hard. the working. Good afternoon, everyone. So, this is regarding distributed RNA system and multi-user microsystems. So, you can see in the figure, there's a one base station transmitting n number of beams, and the RIS, reconfigurable intelligence testbeds are deployed in distributed manner. So, this is the first RIS, and key RIS element. And these are the key users. So it means we are using two fields for one user. The first field is direct coming towards user. Okay, you can see here is called the second one is coming through the this RIS. So this means the base station is serving one user with two beams. Okay. So if they have k users, we require two k beams. Okay. So now we have problem how to adjust the phases of each RIS. So the signal will go towards the user. Okay. So now you can see. So these are channel models. These are channel models that we are using. And this is the final expression for input-output relationship. So what is the main task coming here? How to adjust the phases? Okay. So yeah, this part. Okay. So this is signal related to this part. We can see coming to the wireless and is a direct feed from the base station to the user. So we are getting the same copy of the signal from two different paths. But how to add up all these two signals? So we're going to combine all these two signals in an optimal way. Okay, it means these signals should be added coherently. Okay. So by using this concept, we are calculating the impedance of the RF element for each user. Okay. So this is how we can compute the phases of each element. Okay. Now after the adjusting the phases in optimal way, we have to choose the beams. It means there are n number of beams, and each user is being served by two beams. So it means we require 2k beams. So we have to select 2k beams out of n beams. So we have used maximum weight matching concept. Okay, it means the beam should be the best beam should be assigned. Yeah, we can say the best 2k beam should be chosen. Okay, based on the maximizing the signal to noise ratio. Okay, so this is nothing but xkn and wkn. Xkn is corresponding to the wkn is the weight. When the beam is chosen, the weight will be 1. Otherwise, weight will be 0. And here we also put the constraint that the beam should be chosen exclusively. It means if you have chosen two beams for a particular user, those two beams cannot be chosen for the another users. So these are the conditions that we are putting here. So after putting all this condition, we have chosen, here you can see beam and users. Okay, we have mapped that and we have selecting the exclusive beams for each user. And after choosing the exclusive beams, we are doing the pre-coding. Pre-coding means we are going to nullify the interference at the receiver side by using the pre-coding at the base station. And then finally, we are going to the power location in the okay. And the power location we can do in different fashion. So I've chosen in this paper. I'm doing the power location in the max min fashion. It means it is not like that I'm giving the more like a unlike a water filling algorithm. There is a particular minimum power should be given to the weaker user. Okay, otherwise there is no meaning of max min fairness. Okay. So now you can see these are the results. Okay. And you can see in these results. So this is the upper bound. Okay. And now you can see the this one. This is the proposed one. Now you can see the proposed one. The proposed one, which is coming higher than the existing algorithms. And this one is in equal power. It means we are giving the equal power to all the users. Okay, till now I did not use the max mean fairness algorithm. Now in the second figure, you can see. So there are two cases with equal power cases with random case with equal power with optimal case. So in this case also we are going to give it equal power, but there are two cases. For first case, I am using optimal case. In the second case, I am using the random cases of the RIS. So you can see the difference. So when you see the optimal case, you can see the expected efficiency and increase the number of it is not much improving, but we are using the optimal cases. So you can see the expected efficiency much improving with increase in the number of passive elements. Okay, so this is the result, and the last one is energy efficiency. Obviously, that we are going to improving the energy efficiency by choosing only the beams which are only useful for the users. Okay, it means we are not using all the beams. Otherwise, we have to continuously give the power all the users. If the two beams are useful, so I will choose only two and give the power to only those two beams. So this is just energy. Now there is one more thing is here. There is one more figure. Yeah, this is the figure. Okay. So now I have also applied max in fairness and algorithm. You can see here. There is a purple one and the brown one. So what would difference the 20 DSR and 15 DSR. So here I am calculating the effective efficiency of the worst user. Okay. How low spectral efficiency can we get? Now, so this equal power allocation you can see here. Okay, so the minimum average spectral efficiency for the power location, and this is one for minimum average spectral efficiency for max min fairness. See, so you can see the effect when we are using the max min fairness algorithm. The base station is applying the fairness algorithm. Okay, it is not like that. Okay, if you are the stronger, so I will give the more power. Okay. So I will put the base station putting a constraint. Okay, this user at least should get minimum data rate. Okay. So by putting this constraint, we can see that this is maximum and this is for equal computation. Okay. And this is for minimum average spectral accuracy. It means it is for the worst user. Okay, whose channel is not every time very good. Okay. But still we are giving a sufficient, you know, still is getting a sufficient data. If you compare to the it is full power. Okay. So this is the concept of the maximum fairness algorithm. So this is from my side. Any question from any audience you can ask. We are simply calculating the quality of error. Okay. Quality it is generated to be that one threshold value. The high ratio should be not be lower than the threshold value. So And then the outtakes, the computer outtakes property of the status key.
Thanks. Anyway, I'm on no problem. Thank you very much.